Welcome to the video lecture series for Texas A&M University course Math 152. Today we will take a look at section 10.4, Other Convergence Tests. You can find the accompanying handouts at bit.ly/RaeleneMath152. Let's begin. To warm up, write the following expressions in order from smallest to largest as n approaches infinity. Exponential functions, factorial functions or expressions, power functions or expressions, and hybrid functions or expressions. Recall that hybrid is a term that I've been using to represent when there is a variable in the base as well as in the exponent. Between exponential and power functions, we know that the slowest growing is the power function, and we know the next biggest is the exponential function. And just to remind ourselves about the difference between factorial and hybrid, let's consider the limit as n approaches infinity of n factorial over n to the n. Doesn't matter which direction I make this quotient. I could put the hybrid in the top and the factorial in the bottom. Then when we expand this, we know that the factorial means n times n minus 1 times n minus 2, etc. all the way down to 0 factorial, which is 1. So I'm not going to write 0 factorial, I'll just end at 1. And n to the n means n times n times n times n number of times. And so here we can see that there are n terms and n factors in the top and n factors in the bottom. So each of these is going to pair up as different quotients, and we can see that the first pair reduce, and then n minus 1 over n has a limit value of 1, so does n minus 2 over n. But eventually there will be some point along this basic pairing up of numerator and denominator where the numerator is substantially smaller than the denominator because the numerator is constant, 3 or 2 or 1 or 4 or 5, etc. And the denominator, n, is approaching infinity. So we can see that the denominator is going to exceed the size of the numerator, and this limit will be 0. And so what we see here is that the factorial function is the next fastest growing, and this idea of a hybrid function or hybrid expression, meaning variable in the base and in the exponent, is the fastest growing. In number 2, write the nth general term an of each series and express the series in sigma notation. Well, what we're looking for here is to do some patterning. So let's take a look at 2a. We have a series where the argument of the sine function is changing, and so there are two things that we want to do. We want to identify each term with an n value, so we have n equal to 1, or we could start at n equal to 1 or n equal to 0. We could start at lots of different integer values, but it's very practical to start at n equals 1, then n equals 2, then n equals 3, etc. And from that we can see that the expression an is going to be sine of n, and therefore the series is equal to the sum from n equals 1 to infinity of the an term or expression sine n. In part B we have the series 1/4 plus 2/9 plus 3/16 plus 4/25 plus dot dot dot. And so to start seeing the patterning, we may want to see another way to write 4, 9, 16, 25, something that they have in common. And we can see that they are perfect squares. So now it might be practical or helpful to identify an n value. We could start off with the first term being n equals 1, and then n equals 2, and then n equals 3, and then n equals 4, etc. Or we could start off with the first term being n equals 2, for example, n equals 3, n equals 4, n equals 5, etc. So if we do that, we could express this series, well, we could express the nth general term for an as the numerator is n and the denominator base is what's changing. The exponent, you'll notice, is constant in the denominator, and so the base of the denominator is n plus 1 each time. So we could say that we have n over n plus 1 quantity squared. Or we could say that an could be the n is the denominator's base, but then the numerator is 1 less than that. So we have n minus 1 over n squared. And either way, we can either get the red sum, so the series is equal to the sum from n equals 1 to infinity of the red expression, which is equal to the series from n equals 2 to infinity of n minus 1 over n squared. So there's not only one way to write each of these, and you have to see what part of each term is changing, identify the pattern, and then associate some n values with it. So I'll leave you to try parts C and D on your own. You might want to come up with more than one expression to get more practice and more exposure to different approaches of writing the nth general term. In number 3, we have some alternating series, because a series in which the signs of consecutive terms alternate is called an alternating series. We are going to refer to an alternating series with the general term an as equal to some -1 to an n or n plus 1 or some value here times bn. And so if we take n equal to 1 to infinity, we can see that bn is equal to the absolute value of an. The an has the pluses and minuses built in, the bn do not, and separating the bn from the pluses and minuses, we see that we have this expression. Okay, so in number A, or 3a, we have the series 1 minus 1/2, plus 1/3, minus 1/4, plus 1/5, etc. This is the alternating harmonic series. We recognize the terms 1 over n, but with an alternating sign. And so to write the general term, we know that bn is equal to 1 over n, and we just need to note if this is going to be n or n plus 1, depending on whether we start with positive or negative. So depending on whether we start with positive or negative, we will either have n or n plus 1 as the exponent. So I'm just going to write n here, or n plus 1. It's a bit crowded. And I'll write it like this, n or n plus 1. Okay, so since we're starting with a positive term in this series, we know that we need the -1 to have an exponent that leaves a positive for the first time. So what that really means we need to do is decide what the values for n are. When we have the first term, n is 1, then n is 2, then n is 3, etc. And so bn is equal to 1 over n, and so we can come up with the sum of the series by adjusting the exponent on the -1. So we're going to say n equals 1 to infinity of -1 to the something times 1 over n, or simply -1 to some exponent over n. And the exponent that we need has to make the first term positive, so if we chose just n, we would have -1 to an odd, which would be negative, so we need n plus 1. Okay, I'm going to leave you to try the remaining ones on your own. Make sure that you account for the alternating piece by using -1 to an exponent that varies. In number 4, consider the harmonic series 1 plus 1/2 plus 1/3 plus 1/4, etc. and the alternating harmonic series as well. In part A, we are asked to write the nth general term for the series, so go ahead and try for yourself. So for this one, we know that an is equal to 1 over n, and for the alternating harmonic series, we know that an is equal to -1 to the n plus 1 times 1 over n, or as we said, over n in one step. And part B says to express each series in sigma notation, So the harmonic series is equal to the sum from n equals 1 to infinity of 1 over n, and the alternating harmonic series is equal to the sum from n equals 1 to infinity of negative 1 to the n plus 1 divided by n. And in part C it says that one of the series converges and the other diverges. We don't really know that one of them converges yet, but if we're told that, we have to come up with an argument to explain which is which. Well, despite the fact that we already know the harmonic series diverges, we have seen the p-series test, and with p equal to 1, we know that this series will diverge. Similarly, that's the same as the integral test, because we know that the integral from 1 to infinity of 1 over x dx diverges, and we can figure that out by evaluating a limit as t approaches infinity for the integral. But we also saw that the sequence of partial sums for the harmonic series was an increasing sequence without bound. And because there was no bound for the Sn partial sum sequence of the harmonic series, we know that the harmonic series will diverge because the limit as n approaches infinity of Sn for the harmonic series was not finite. But apart from that, if we just think about these two different series, we see that the blue series is going to continue to add numbers, whereas in the red series, every second term is going to subtract. So we have an idea or a sense that the red series is smaller than the blue series. We cannot really use the comparison test on this because the comparison test from 10.3 only works if all the terms are positive. So we can't really compare the alternating harmonic series to the harmonic series or vice versa because the comparison test works when an is positive. And so that was from 10.3. And so, but a sense of the comparison test says that the harmonic series is greater than the alternating harmonic series. So if we happen to know that one series converges and the other diverges, this is really enough to say that therefore the harmonic series diverges and the alternating harmonic series converges. In number 5, we want to let the sum from n equals 1 to infinity of Bn be a non-alternating series. So remember that we are going to take Bn as the expression over here, we said, to be the positive terms, and then the negative sign comes from this negative 1 to a variable exponent. So we have the Bn, sum of Bn is the non-alternating series, and we also want the Bn terms to be decreasing. We're going to let the sum from n equals 1 to infinity of An be the alternating version of the Bn series. In other words, that Bn is equal to the absolute value of each An term. So in part A, which series has the greater sum? Well, this is what we were just talking about. We have that the sum from n equals 1 to infinity of An is equal to A1 plus A2 plus A3 plus A4 plus dot dot dot. But this is really an alternating series with terms B1 minus B2 plus B3 minus B4, etc., such that Bn are all positive numbers. So we know that Bn are all positive because we have a non-alternating series. It is true that all the Bn values could be negative, so we have negative, so that this is all the Bn terms are negative, so that would be a negative sum if finite. But it's easy enough just to say Bn is positive, and if we wanted all negatives, we could factor a negative in front of the sigma. So then what we have is for the other series, for the sum of Bn terms, we get B1 plus B2 plus B3 plus B4, etc. And the series with the greater sum is the one where the signs don't alternate. So this is the series of Bn is going to be greater than the series of the An. Now, we still can't use the comparison test here for two reasons. One, we don't know the convergence of either of these series. And two, we cannot use the comparison test, rather, when we don't have all positive terms. But in part B, then, we want to talk about an upper bound for the infinite series A6, A7, plus A8, plus A9, etc., knowing that the Bn terms are decreasing. So this is really equal to, we know that B1 is positive, B4 is negative, so A6 is equal to negative B6 plus B7 minus B8 plus B9 minus ... And the fact that these terms are decreasing means that the size of the first two terms, for example, negative B6 plus B7, is going to be at most, in magnitude, the amount of B6. But I don't need absolute values around B6 because B6 is already a positive term. And so if I were to take a look at the next three values, the biggest that this would be is to the left a bigger amount, to the right a smaller amount, to the left an even smaller amount, because going left B6 and then right B7, if the Bn are decreasing, we're not going back in the reverse direction as far as we had come. And so we know that the green amount is also at most B6, and so is the value of all four of these terms. It's in magnitude at most B6. And so what we're seeing is that the most away from where we started that we will end up is B6, either to the left or to the right. So an upper bound for this value, I'm just going to move this small diagram down. In magnitude, this amount is at most, so it is less than or equal to the value of A6 in magnitude. But A6 in magnitude is equal to B6. So therefore B6 is an upper bound for all of these values. Now in 10.3 we studied the convergence of series of terms that are all positive. We will now consider the tests for the convergence of alternating series. So in this case the signs of consecutive terms alternate, meaning there are not two or more consecutive positive or consecutive negative terms in the series. So let's look at some definitions. The definitions of absolute convergence and conditional convergence state: if we let the series, or the sum of an, be an alternating series, then we can talk about absolute convergence and conditional convergence as follows. I'm going to refer to the sum of an as the alternating series, and then the sum of absolute value of an as the associated non-alternating series. So if we know that the non-alternating series converges, and the non-alternating series is bigger than the alternating series, because the alternating series subtracts some terms every other term. If the non-alternating series converges, then the smaller alternating series is called absolutely convergent. Of course, if the non-alternating series converges, of course the smaller series will converge. And so absolute convergence is both when the alternating series and the associated non-alternating series both converge. However, if the non-alternating series is too big, meaning that it has an infinite sum, however, the alternating series is small enough to have a finite sum, we say that the alternating series converges, but the non-alternating series diverges, and so the alternating series is conditionally convergent or just convergent. So if we just say convergent without any further word in front, then we do not mean absolutely convergent, we mean conditionally convergent. So what this definition of absolute versus conditional convergence has to talk about, it's really about the rate at which the an terms converge to zero. Recall that by the nth term test for divergence, the nth term test for divergence says unless, well, let me write it this way for the words to be clearer. If the limit as n approaches infinity of an does not equal 0, then the series of an cannot possibly converge. So what we're saying is that the terms of the an sequence, and therefore the terms of the series, must have a horizontal asymptote of the y-axis. This is n equal to 0 or x equals 0. And so unless the terms have a horizontal asymptote, it is not possible for the series to have a finite sum. But even though the limit as n approaches infinity of an does equal 0 in some cases, the terms do not approach a height of 0 fast enough in order to have a finite infinite series. And so the rate at which the an terms of an absolutely convergent series converge to 0 is much faster than the rate at which the terms of conditionally convergent series converge to 0. So we're talking about the strength or the rate of growth or decay of the convergence of an alternating series when we talk about absolute versus conditional convergence. Number 6 we want to know, is the alternating harmonic series absolutely or conditionally convergent? Well, let's take a look at absolutely convergent first. And before we actually look at that, let's just talk about the series, the alternating harmonic series, AHS, equal to the series AN, which is given by the sum from n equals 1 to infinity of negative 1 to the n over n. So we have, negative 1 to the n plus 1. So 1 minus a half plus 1/3 minus 1/4 plus 1/5. It's an alternating p series with p equal to 1. So is this absolutely convergent? If so, then the series of the absolute value of an terms converges. So we ask, does the series from n equal 1 to infinity of, when we're taking the absolute value, you just don't need to write the negative 1 to the variable exponent part. So we have, does the series of 1 over n converge? Our answer is no, because this is the harmonic series, which as a basic series we know diverges, which is a p series, we could say. With p equal to 1. Okay, so we know that, therefore, the alternating harmonic series is not absolutely convergent. And so we want to now test if the alternating harmonic series is conditionally convergent. Even though the non-alternating series doesn't converge, can the alternating version converge? And the answer to that is, we still do not have a test. We still do not know if this series will converge or not. We need a test. And so the next test we come up with is the absolute convergence test. First of all, we'll state that if the series of the non-alternating terms an converges, then the series of an, the alternating version, must converge. So we know that if we have a strong enough series growing or approaching the horizontal asymptote of an equal to 0 or y equal to 0, then the alternating version converges because it is smaller than the non-alternating version. So verbally this says that if a series is absolutely convergent, then the same series must be convergent. Okay, so let's show that the series from n equals 0 to infinity of negative 1 to the n over n root n converges. I'm just going to rewrite this as the series of an and rewriting it in terms of an exponent in the denominator of 3/2. Therefore, we have that the series of absolute value of an, or the series of bn, we are generally going to take bn to be positive terms. Therefore, the absolute value of an can be referred to as the bn terms. And here, this series from n equals 0. Actually, that's a typo. We can't start this from n equals 0 because we have a vertical asymptote or a discontinuity. So let's change that to n equals 1. And I'll change that in the handout. N equals 1 to infinity of 1 over n to the 3 halves. This series converges by the p-series test because p is equal to 3 halves, which is greater than 1. And so we know that the Bn series, since the Bn series is greater than the alternating series, then by the absolute convergence test, we don't really need to state this. I'm just putting it there as a reminder for us. So I'm actually not going to use it as part of the conclusion. I'm going to write note. The series of Bn is greater than the alternating series of An terms. And so we can conclude by the alternating series test, rather, by the absolute convergence test. I'm jumping ahead of myself. We know that, therefore, the series from n equals 1 to infinity of negative 1 to the exponent n divided by n root n also converges. In other words, we can say that the given series is absolutely convergent. Okay, this test still doesn't help us with the alternating harmonic series because the harmonic series is not convergent. So now we have one more test for dealing with the alternating harmonic series. This test is unique compared to the other ones because it is actually not a comparison of an unknown series with unknown convergence behavior to a series with known convergence behavior. So what we have here is a series test which is based solely on 3 conditions. If our series that we are testing for convergence satisfies or meets all of the conditions, A, B, and C, the 3 conditions, then by the alternating series test, our alternating series converges. So if we have an alternating series made up of An, where An is the negative 1 factor for the alternating part, times Bn, where Bn are all positive, this series will be convergent if the following conditions are satisfied. Well, the first condition is stating that the Bn coefficient or terms are positive. In other words, the negative of the term is coming from negative 1 to the n plus 1, not from Bn. And you will be able to recognize from expanded form if this condition is satisfied because we have alternating signs and not 2 or more consecutive positive or consecutive negative terms. Okay, so if we had positive, positive, negative, negative, then we would not satisfy condition 1, or condition A. Condition B says that Bn is greater than or equal to Bn plus 1. Well, what we're really saying is that the terms that are earlier are bigger or the same size as the later terms. In other words, the later terms are only not bigger. And so we have that the magnitudes of terms is non-increasing. There's a typo there. That should say increasing. And so we have second condition being met. Let's just go on to the third condition. The third condition says that the limit as n approaches infinity of Bn must equal 0. This sounds like the nth term test for divergence, which on its own does not lead to a conclusion about whether or not a series converges. We do know that if the limit as n approaches infinity of Bn, or any series term, An, is non-zero, that the series diverges. But we did not have a conclusion if the limit was 0. Now, taken together, conditions C with conditions A and B for alternating series, these three conditions taken together, as opposed to one by itself, are enough to state that the alternating series converges. So this is saying that the right-end behavior is a horizontal asymptote for functions for f of n equal to b sub n of y equal to 0. So if we have a horizontal asymptote, the terms are not increasing, and the terms are alternating in sign, then the alternating series converges. So now let's apply the test in number 8. Do the following alternating series converge? If so, do they converge absolutely? And explain. In part A, we have the alternating harmonic series yet again, where n is the sum from n equals 1 to infinity of negative 1 to the n plus 1 all over n. So this is equal to the sum from n equals 1 to infinity of negative 1 to the n plus 1 times 1 over n. This tells us that the Bn part, without the negative 1 alternating sign part, is equal to 1 over n. So now we're going to test the conditions. The three conditions, first of all, state that Bn are always positive. And here, Bn is equal to 1 over n, which is always positive, for the n values we have, greater than or equal to 1. So this is true. The second condition is that the Bn terms do not increase. So we know that Bn is equal to 1 over n, and we know that Bn plus 1 is 1 over n plus 1. So this implies that the bigger the denominator, the smaller the fraction. And so 1 over n is greater than 1 over n plus 1, which implies that Bn is purely greater than Bn plus 1, and so condition 2 is true. The third condition involves looking at the limit as n approaches infinity of Bn, and Bn is 1 over n, and that limit is 0, so the third condition of the alternating series test is true. So we simply conclude, since all three conditions are satisfied, therefore by the alternating series test, the sum from n equals 1 to infinity of negative 1 to the n plus 1 all over n, also known as the alternating harmonic series, converges. And when we say just converges, we mean conditionally. We know that this series does not converge absolutely because the non-alternating version of this series is the harmonic series, which is divergent by p series equal to 1. So I'm going to leave you to try parts B and C on your own, and you can check the final answers with the completed lecture notes. We have then an estimation theorem for the series found, the series error term coming from an alternating series. If an alternating series satisfies the three conditions of the alternating series test, and by that we mean, therefore, the alternating series converges. So for a convergent alternating series, then the maximum value that the error, Rn, can be is given by the magnitude of the n plus first term. So let's just think about that again before we try example 9. If we have S is equal to A1 plus A2 plus A3 plus A4 plus ... plus AN plus AN plus 1 plus an plus 2 plus dot dot dot. This could be written as b1 minus b2. Of course, the first term could have started off as negative, but we could just adjust that by changing the exponent on the negative 1. So we can write some terms here. I'll put plus a1 here, it doesn't really matter, rather plus bn here. I don't know if n is odd or even, so I don't know if this is positive or negative. But then if this is plus bn, this is minus bn plus 1, plus bn plus 2, minus dot dot dot. And we know that this first part here, the sum of the first n terms is called Sn, and then the remaining infinite series is the remainder after the first n terms called R sub n. Even though it's the beginning of the n plus first term, we don't call it R sub n plus 1. And so now we know that Rn is going to equal S minus Sn, where S is the exact value of the series, the exact sum, and Sn is the approximate after n terms value of the series. It's the nth partial sum. And Rn is the difference between them, so Rn is the error between the exact, which we don't know, and the approximate value that we can work out. So we want to have an upper bound. What's the maximum that the error can be? What's the maximum distance away from the exact value that the approximate value can be? Because we want to know if our approximation is any good. If it's not any good, we need to use more values in the partial sum, so we need to use a bigger value for n to approximate Sn to give us the exact S value. Well, because we have an alternating series that satisfies the alternating series test criteria, we know that the values of bn plus 1, bn plus 2, bn plus 3 do not increase, which means that when we are coming up with a diagram for these values, bn plus 1 is positive, so negative bn plus 1 is going to the left. And so if we go to the left an amount of bn plus 1, the next term says go to the right an amount of bn plus 2. Now bn plus 2 might be exactly the same value as bn plus 1, or it may be less than the value of bn plus 1. So we may go all the way back and have that these two terms actually cancel out, or they leave us with a little bit left over. What's the maximum that that blue distance can be? Especially if we keep adding terms and we keep going back and forth and back and forth. Well, the maximum that this original blue distance can be is the same as the full green distance. So we're seeing that Rn is at most bn plus 1. And at most means that Rn is going to be less than or equal to bn plus 1. And so this is the idea of the alternating series error estimate. You simply need to say, because the series satisfies the alternating series test conditions, that the Rn is less than or equal to the magnitude of the bn plus 1 term. In number 9, we want to approximate the sum of the series to 3 decimal places. So what we want is for S, which is to be given by Sn plus Rn, to be approximated. We want S to be approximated by Sn. And what we need then is that the difference between S and Sn, which is the remainder, to be at most some number. Well, what is that number if the difference between these two things is at most 3 decimal places? Well, we do need to think about the difference. We don't know if S or Sn will be bigger. So we don't care about whether we're different, the Sn is bigger or smaller. So we're just going to talk about the magnitude of the error, which means the magnitude of Rn. So we don't care whether Rn is positive or negative. If Rn is positive, that means that Sn is bigger than the actual exact S value. Well, in order to find out what this bound is for Rn, I need to know how do these numbers subtract to be accurate to 3 decimal places. So if I have a number that is 0.843217, for example, and let's call that S, and I subtract a value, and I want it to be accurate to 3 decimal places, that means that the 8, the 4, and the 3 have to be the same. Which means that the first digit or decimal place where they can be different is in the 4th one. Now, there are lots of different numbers that can be here, but I want to know the smallest possible value for this difference, and that means that these numbers would be off by at most 1 digit. So this could be a 1 or it could be a 3, and so then the maximum amount of error I'm expecting is 0.0001. Of course, if this is a 9 in this second digit, in this 4th digit, then I would have 0.007, but I would still be accurate to within 3 decimal places. So the maximum amount that I'm looking for Rn in magnitude is 0.000 and then a 1. Notice that if this gets any bigger, 0.009 and then a little bit bigger makes it 0.001, which means that I don't have the same third digit in the decimal places. So I'm not going to be looking at any other maximum error except for 0.001. But by the alternating series error estimate, I do have a value that Rn is given by. But I do have to be careful here because I can't just use the alternating series error estimate for any alternating series. I must make sure that the 3 conditions are satisfied. So my 3 conditions are my Bn term, which is equal to 1 over n factorial, without the negative 1 to the n, is positive for n greater than 0, greater than or equal to 0. Recall that 0 factorial is equal to 1. My second condition says that Bn, which is 1 over n factorial, has to be greater than or equal to Bn plus 1. So Bn is equal to 1 over n factorial, and Bn plus 1 is equal to 1 over n plus 1 factorial, which is a bigger denominator, and therefore a smaller fraction, and so this is purely positive, or purely greater than, which means that the second condition is true. My third condition states that the limit as n approaches infinity of Bn must equal 0, and the limit as n approaches infinity of 1 over n factorial does indeed equal 0, so the third condition is true. And so therefore, the alternating series error estimate for Rn is at most, for the magnitude of Rn, is at most the b sub n plus 1 term. So what we want to find out is the n value that makes Bn plus 1 equal to 0.0001. So now we want to solve for n such that Bn plus 1 is equal to 0.0001. Bn plus 1 we know is 1 over n plus 1 factorial. And this is not a solution that we can find by hand, so we can look graphically or we can use some kind of graphing program. And if we do that, first of all, I'm going to reciprocate both sides. I have that n plus 1 factorial. If I reciprocate the left, I reciprocate the right. And the right-hand side is 10 to the exponent of 1, 2, 3, 4, negative 4. So we get 10 to the exponent 4 in the reciprocation. If you didn't know how to solve, we could simply plug in some values for n and see what happens. We know that if n is 4, then 5 factorial is 120, and this is 10,000. So we need to come up with a bigger value than n equals 4. So you could just plug in a few values and see what happens. And so we could say, what's 6 factorial? What's 10 factorial? Okay, that's far too big, so what's 8 factorial? 40,320. What's 7 factorial? 5,040. So we know that we have to have n has to be, or rather n plus 1 has to be 8 to be at least as big as this value. since we know 7 factorial is 5,040 and 8 factorial is 40,320, let's write that down. 7 in red. 7 factorial is 5040, and 8 factorial is 40,320. We know that we need n plus 1 to be big enough. So let's actually go back and use our inequalities, because I think this will make it clearer for us. So for our inequalities, we knew that we want Rn to be at most Bn plus 1. So Bn plus 1 has to be at most, which means less than or equal to this value. But then when we reciprocate, the reciprocal will be greater than or equal to. So we need n plus 1 to be greater than or equal to 10,000. And if n plus 1 is equal to 7, then n plus 1 factorial is not greater than or equal to 10,000. So we need n plus 1 factorial to equal 8 factorial, which means that we need n to equal 7. And so the question, if we go back and look at it, says to approximate s to 3 decimal places. Well, we were going to approximate s by Sn, and we couldn't find the value for Sn until we had the value for n. So we were given a condition about Rn, which helped us to work backwards to solve for n. So knowing something about Rn helped us to solve for n, so now we can substitute the value for n and come up with the partial sum approximation. So now we know that s will be approximated by s subscript 7, which is equal to the sum, and we're going to go from n equals 0 until what? Well, we want the sum of the first 7 terms, or do we want n equal to 7? We're actually choosing n equal to a value of 7, starting from 0. So we want n equal to 0 to 7 of negative 1 to the exponent n all over n factorial. Let me just double check my exponent. Negative 1 to the n. And so we can use a calculator to work this out. And so in the summation, we have n equals 0 until 7 of negative 1 to the exponent n divided by n factorial. And we can approximate that to a decimal if we want, but there's no problem leaving it as a fraction, which is tidier and exact. So we'll put this in the lecture notes. And so we can see the value for Sn, which is going to be 103 over 280, and therefore S7 equal to 103 over 280 is an approximation to S equals the full series, the full sum value, the infinite sum, correct to 3 decimal places. So let's just take a look to see what happens in the graphing calculator if we actually did try to approximate this value of the infinite series using more n values. And I'm just going to approximate in one step. We're going to get 0.3678. So in fact, these two are still correct to 4 decimal places, and we only wanted to be correct to 3 decimal places. And if we use 9, we see that the 4th decimal place is still correct. Well, what would have happened if we had used 6 for the top bound? And then when we approximate, we get 0.368. And we see that for the first time, using n equal to 6, that the 3rd decimal place is different. And we didn't want the 3rd decimal place to be different from the exact. We wanted it to be the same. So in fact, we could not use n equal to 6. Okay, Well, there's one last test that we are going to look at, and it's called the ratio test. The ratio test is the test that we will be using in 10.5 and beyond to determine the convergence of a series, but also the radius of convergence of a series, which we need because we are going to look at how infinite series can represent functions, and then we can use the radius of convergence to talk about the domain of those functions. So later on we are going to relate series to continuous functions, and we will be using the ratio test a lot in 10.5, 6, and 7. So the ratio test says to let the series an be any series with positive terms. And we are going to let L be the limit as n approaches infinity of the absolute value of an plus 1 over an. This could all be in one great big absolute value. So we know that the value for L will only be positive. And so if L is between 0, if L is less than 1, being a positive number, that means that L is between 0 and 1, then the series converges. But if L is more than 1, then the series diverges. It's possible that the limit is equal to 0, so we could have from 0 to 1 inclusive or greater than 1. But if the limit value is equal to 1, the test is inconclusive. We have seen inconclusive tests before when we used the nth term test for divergence. We had, if the limit as n approaches infinity of 1 over n is equal to 0, then this 0 limit does not tell us whether or not the series of an converges or diverges. We still don't know. However, we've also seen with the comparison test, if the series of an converges and the series of and bn terms are greater than an terms, then the series of bn converges or diverges. So we've seen a couple of cases of having inconclusive tests. So the ratio test will also be inconclusive if the limit value is equal to 1, and we will need to use another test to determine if the series is convergent. So let's go through an example of this one to see how the ratio test works. In number 10, test the series given for convergence and absolute convergence. So we are going to use the ratio test here. So the first thing we're going to do is decide to work out the value for L, which is the limit as n approaches infinity of the absolute value of an plus 1 over an. Now, as soon as we have the absolute value, we no longer need to involve the negative 1 to the n part of the expression. So we are going to consider that when we divide by an, that's the same as multiplying by the reciprocal of an. So we're going to have an plus 1 multiplied by 1 over an in the absolute value. So the L value is the limit as n approaches infinity of an plus 1, which is n plus 1 squared, divided by 2 to the n plus 1, and then multiplied by 1 over an. So the reciprocal of an is 2 to the n over n squared. And so now we are going to see that n is greater than or equal to 1, so the absolute values are not necessary. So I'm going to drop the absolute values, and I'm going to expand this a little bit to help me see evaluation of the limit. And I'm going to put the power terms top and bottom together, and then I've got 2 to the n divided by 2 to the n times 2. So we can reduce the 2 to the n top and bottom, and we can take the constant 1/2 in front of the limit. And now we go back to pre-calculus and to end behavior on the right-hand side. We have a quadratic divided by a quadratic, and so the limit as n approaches infinity of this particular rational function is going to be 1. So we get 1/2 multiplied by 1, which is equal to 1/2. What we're seeing is that the limit is equal to 1/2, which is contained from 0 to 1, and therefore the series of an converges. And the truth is, this was conclusive whether or not we had the negative 1 to the n or not. So this is actually saying that this converges absolutely and therefore also conditionally. So we have that the series of the alternating series converges and the non-alternating series also converges. In other words, the given series converges absolutely. Just to kind of understand the ratio test a little bit better, let's consider another simple type of series that has a ratio involved. Let's go back and recall the geometric series. A geometric series is a series of the form a times r to the n minus 1 for n equals 1 to infinity, and it is a plus ar plus ar squared plus ar cubed plus dot dot dot, and it's equal to the sum of a over 1 minus r if r is contained from -1 to 1. And what we see is that not only do we have a ratio of r, but we have a common ratio of r, where we multiply each previous term times r to get the new term. So the common ratio of r is kind of a special case of having a ratio. This means that a2 divided by a1 is equal to a3 divided by a2, which is equal to a4 divided by a3, which is equal to, etc., an plus 1 divided by an. And that ratio is always equal to r. Contrasting that, the ratio test and what we saw for convergent series in general is that we are going to have the limit. Well, let's recall what it means for a sequence to converge. If a sequence converges, then the limit as n approaches infinity of an minus 1 equals the limit as n approaches infinity of an, which equals the limit as n approaches infinity of an plus 1. In some sense, what we're finding is that there is a ratio between one term to the next. And we may say that a2 over a1 is a certain ratio, but it may not in general equal a3 over a2, which may not in general be a4 over a3, etc. But if a convergent series an, or if a series an converges, then as n approaches infinity, an plus 1 over an does equal an over an minus 1, because we're getting the same end behavior eventually. So while we do not have a common ratio throughout the entire series, and the series is given by a1 plus a2 plus a3, etc. While we don't have a common ratio, in a sense, later on, we will have a common value from one to the next, which is the limit value. And so this limit value of L that we are using in the ratio test is like the common ratio of R, which had to be between -1 and 1. And so we're seeing that this behavior from the ratio test, that L has to be between 0 and 1, keeping in mind that L is only positive or 0, because it's the limit of an absolute value expression, then we're saying without the absolute value, L could be between -1 and 1. And if L is beyond 1, then the series diverges. However, if L is equal to 1, then we might have some alternating behavior which could produce some conditional convergence. We will explore this idea of the ratio test further in 10.5 when we discuss power series. Well, this concludes section 10.4, Other Convergence Tests. Please make sure that you have completed the handout and prepared a list of clarifying questions about the lecture. That's all for now.